So this week, we're starting our new unit, which is chemical equilibrium. Chemical equilibrium is very important to the world around us. So far, we've only looked at reactions that occur in one direction. All of our arrows have kind of been, those quantitative arrows mean the reaction goes to completion. However, in reality, most reactions, or a lot of reactions that occur are actually reversible. So as reactants form products, products break down to form reactants. And this is what's called chemical equilibrium. Chemical equilibrium is at play in what's called the Haber process. The Haber process uses 1% of the world's energy, and the whole point of the Haber process is to take nitrogen from the air and form ammonia. The reason why this is important is because plants cannot absorb nitrogen from the air, but they can convert ammonia into forms that they can use. So this is actually a process that produces fertilizer, and without it, we wouldn't be able to feed a majority of the population. So it has been a very important chemical reaction, but why do we need to use so much energy for it to occur? And that's going to be something that hopefully becomes more clear as we go through this unit looking at chemical equilibrium. So here's an analogy for equilibrium. Here I have my reactants, here I have my products. And then I have these two straws which represent the reaction rates. Now in a equilibrium system, these reactions are reversible. So as my reactants become products, my products are turned into reactants. Now this system is dynamic. So it continues on and on. So as my reactants become products, my products are also being converted into reactants. And you'll notice that initially, these rates aren't the same. I have far more reactants becoming products than I do products becoming reactants. Eventually, though, these rates are going to get closer to each other. As time goes on, these rates become similar until the point where these rates are the same. So my amount of reactants becoming products is equal to my amount of products becoming reactants. That is when equilibrium is established. At that point, the concentration of my products and reactants, so the amount that I have, is not going to change. The things that depend on concentration, things like pH, color, pressure, are not going to change as well. So from an outside, from a macroscopic perspective, looking at this system, it looks relatively stable, like nothing's changing. If you were to zoom in to the molecular level, you would see that this chemical reaction is still occurring. So my reactants become products, as my products become reactants. This doesn't stop. However, because these rates are the same, as observing from the outside, everything looks like it's not changing. That's chemical equilibrium. So a reversible reaction that is dynamic, so it doesn't stop. And it occurs when the rates of the forward and the reverse reaction are occurring at the same time, at the same rate. There are a couple things that need to happen. So in that previous example, you saw kind of what it looks like, that it's dynamic, it's constantly occurring. So chemical equilibrium is a dynamic system. Now, this has to occur in a closed system. If we lose products or reactants, then this system is not going to be at equilibrium any longer. So it has to be a closed system. We say that chemical equilibrium is dynamic, meaning that as reactants become products, products also become reactants. That never stops. At chemical equilibrium, so when we reach equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. So it's all about those rates being the same. Concentrations do not need to be the same. If you look at this graph, so we initially started with H2 and N2. So this is the Haber process. We start with hydrogen, we start with nitrogen. As time goes on, they go down and NH3 goes up. Now at equilibrium, equilibrium is the point we reach right here where the concentrations are now unchanged. We see that for the rest of the graph, they're just flat. You see that the concentrations are not the same. They don't have to be. Sometimes they are, sometimes they aren't. However, the rates would be the same. The rates of the forward reaction is equal to the rate of the reverse reaction. So equilibrium is all about rates. Because the concentrations don't change, the other thing is macroscopic properties. So macroscopic properties are things we can see. Macroscopic properties, are unchanged as well. So these are things like pH, that's dependent on concentration, or color, or pressure. Anything that is dependent on concentration is going to be unchanged as well. So when we look at this system, it appears that nothing's happening, but if we were to zoom in, we would see that reactants are becoming products, products are becoming reactants, but the overall concentrations don't change. That is chemical equilibrium. Look at the previous slide. You see, as they change, they don't change by the same amount. And that is because of those coefficients. Hydrogen is going to change by 3 times the amount of, we can read it off a graph like right here, or maybe it's given. Now we can actually quantify equilibrium and identify whether there are more products or more reactants, or whether those amounts are the same at equilibrium using what's called the law of chemical equilibrium, or the equilibrium expression. Now this expression is only for gases and aqueous solutions. So we don't include, no solids or liquids when we actually do these equilibrium expressions. What the equilibrium expression is, it is the concentration of my products over the concentration of my reactants to the power of their exponents. So for the Haber process, so if I wanted to write out the Kc for the Haber process, the concentration of my products goes on top, and whatever the coefficient is becomes its exponent. Now those are important. If you nitrogen, because its coefficient is 3 compared to 1. So those coefficients show up in this equilibrium expression, and they show up as exponents. So my products go on top, reactants on the bottom. So this would be my concentration of N2 to the first power, so I don't need to do anything to it, times the concentration of H2 to the third power. So this is what an equilibrium expression looks like. It is products over reactants to the power of their coefficients. We do not include solids or liquids, so only gases or aqueous solutions are included in these equilibrium expressions. Now, if we know concentrations at equilibrium, so if we know these things, these concentrations when the system reaches equilibrium, us in a question, well, we can calculate that Kc. And that Kc allows us to quantify whether there are more products or more reactants. Products are up top. So if Kc is very large, that means that there's more stuff on top. That means we have more products. Reactants are on the bottom. So if Kc is small, that means that we have more stuff on the bottom. We have more reactants. We're going to be writing out equilibrium expressions. You're going to be analyzing some systems at equilibrium and coming up with equilibrium expressions. And you're also going to be doing some calculations. You're going to be putting numbers in for these concentrations when they're given to us and calculating Kc. Based off of that Kc, we can determine whether there are more products. So if it's large, there's more products, or if it's small, there are more reactants. So looking at the Haber process further, here we have some equilibrium constants at different temperatures. So at 25 degrees, it's 3.3 times 10 to the 8. At 2.6, it's at 177, it's 2.6 times 10 to the 3. And at 327 degrees Celsius, it's 4.1. So the question is, at what temperature would you expect to find the highest proportion of hydrogen and nitrogen? So these are my reactants. If we think about Kc, it is my concentration of my products over my concentration of reactants. So if I'm asked about where I have the most reactants, that's going to be where Kc is the smallest. So at higher temperatures, I have fewer reactants, according to these K values that are given to us. So if we wanted to maximize the amount of products that we make, I guess going back to that last point, so reactants at high temperatures is bad, right? If I am doing this as an industrial process, I don't want reactants, I want products. That's where I make my money. So part of the reason why the Haber process requires so much energy is to actually cool it. So we spend some money to actually cool it down so that we can have higher yields of products and produce more ammonia, so that less of it breaks back down into N2 and H2. So assuming the reaction rates are fast enough so that equilibrium is reached quickly, at what temperature would you design a commercial reactor to operate to maximize the yield of ammonia? So if we want the most ammonia, so that's our number on top. So ammonia is our products. So if we want lots of products, that means we want Kc to be relatively large. So lower temperatures allow us to produce more products. So this week,